Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
To analyze the Doppler effect for sound, we work out a relationship between the frequency shift and the velocities of source and listener relative to the medium, usually air, through which the sound waves propagate. To keep the thing simple, we consider only the special case in which the velocities of both source and listener lie along the line joining them. Let them be the velocity components along this line for the source and the listener, respectively, relative to the medium. We choose the positive direction for both and to be the direction from the listener L to the source S. The speed of sound relative to the medium is always considered positive.
The Doppler effect is defined by this formula. This formula expresses that the frequency that the listener experiences is equal to this product, which is the frequency of the original sound times the division between the velocity of the wave, which in this case is the sound, which has this velocity that we already know, and the velocity plus the velocity of the listener, which is in our case 0 meters per second, divided by the velocity again of the sound plus or minus the velocity of the source, meaning in this case that we are going to represent the car that is moving. And why do we have a plus and a minus here? This comes from the fact that when the car is coming to us with a certain speed and the waves are being dragged closer together, meaning that the frequency that the listener experiences is higher because the waves are closer. And when the car starts moving away from the listener, the frequencies go up. The frequency goes down because the sound waves are further apart, as you can see here. So this is the basics of the Doppler effect. But other important thing that we need to take into consideration is the intensity of the waves that we are listening. When we listen to a car coming to us with its horn, we listen this type of the feeling that we get is that it is coming and it is going. And why do we get this feeling? It's not only because the frequency changes, as we saw here, it's also because the intensity is inversely proportional to the distance to which the listener is from the sound in this case of the car. We're going to do a few examples of what we calculated in this project, and by doing so we first needed to know this term. And we know how did we get this term? Well, the frequency was measured using a software, and what we did was that we put into that software a voice note recording the horn of the car, and the frequency we obtained was 829 hertz, which is between the values that are accepted by a car horn. This value is a constant, so is the velocity of the sound, and the velocity of the listener is 0, which we can cancel out right now. And now we need to go to the only thing that's going to change in every scenario, which is the velocity of the source. We did 4 experiments, and we started in 40 kilometers per hour, and we finish in 100 kilometers per hour. We went from 20 to 20, we increased the velocity 20 kilometers per hour each time, and we passed this to meters per second because all the data here, the velocity of the sound is in meters per second. So for example, if we take the first case, which is where the velocity of the source is equal to 40 kilometers per hour or 11.11 meters per second, we obtain the following frequency from the listener. Remember, we are going to get two different frequencies, one with the positive when the car is leaving or getting further, and one with the negative when the car is coming closer to us. So the first scenario, let's use the case when the car is coming closer. Meaning that if this is 0, 343.2 meters per second divided by 343.2 meters per second plus, minus 11.11 meters per second. All that multiplied by 829 hertz, we obtain that the frequency that the listener got when he was getting when the car was getting closer is, as we already calculated, 856.7 hertz. Remember, this is the frequency that the listener experiences when the car's coming. But what happens when the car's leaving? Well, now we have to apply the opposite. We say that the frequency of the listener is equal to, again, 343.2 meters per second divided by 300.2 meters per second plus 11.11 meters per second, and we obtain times the frequency of the original sound. We obtain that the frequency of the listener is equal to 803 hertz. So as you can see, what happens is that when the car is coming closer, the frequency of the sound increases, and when it is getting farther, the frequency decreases. And the intensity is gonna change through time, and it's gonna look something like this. It's coming, it's at its highest, and then it goes down again. And this same thing we are going to illustrate it 3 more times, but it will be shown in the next graphics.
As we can see, our original frequency 829 coincides with the parameter with the car horn. Also, our graph proves our calculations because the error is minimum. The possible error could be an irregular velocity from the source or noise from the environment. Also, we can see how when much faster you go, the difference from the original frequency are greater.
We can conclude by saying that the Doppler effect depends on 4 components. The first one is the sound source. This one has a unique frequency. The second one is the receptor. Then we have 2 velocity, the velocity of the sound source and the one of the receptor, if the receptor is moving. When the sound source is approaching to the receptor, the frequency is higher, so the listener hears a sharp noise. When the sound source is moving away, the sound is deeper, so it has a lower frequency. This is demonstrated with our previous experiment. If there are different receptors, each one will hear a different frequency depending on the position.
Oh, sure, I see it now, the Doppler effect.